Hello, my name is Braden Wilcom. I am an undergraduate student at Worcester State University, and today I'm going to be talking about aromatic molecules throughout the earliest stages of star formation. So, what is an aromatic molecule and why is it important to us? Well, an aromatic molecule is an organic compound with rings of carbons. For example, benzene in the middle here is a ring of 6 carbons. They are important because they play a vital role in all biological processes, and thus life on Earth could not have existed without aromatic molecules. So that begs the question, how do we get aromatic molecules here on Earth? So in space, we know space is mostly comprised of dust, ice, and gas. And somehow over millions of years, this coalesced to form a planet abundant in aromatic molecules. So we want to know, how did this happen? Where did the most basic aromatic molecules first begin to form? So how do we think they started forming? Well, we think that we saw that in supernovas, um, aromatic molecules get formed when mass amounts of material are ejected from the star as it supernovas. And as that material rapidly cools down, it undergoes complex chemistry and ends up forming much larger molecules than these simple aromatic molecules. But then as those larger molecules get bombarded by the immense amount of radiation that is also released by the supernova, those large molecules get broken down into basic aromatic molecules such as benzonitrile. These molecules then form, we believe these molecules then formed clouds, and those clouds then, over millions of years, formed stars, which then formed planets, and that's how we got to where we are today. However, more modern studies have shown that this process can't be where the majority of these simple aromatic molecules come from, due to the fact that they would continue to be bombarded by radiation for thousands and if not millions of more years. And no significant amount of simple aromatic molecules would survive this process to the point where they could start forming new stars and planets. Only the larger ones that are more hardy against radiation would be able to survive this process, and they're what we believe forms most of the dust in the universe. So when you still look at these intermolecular clouds of dust, we started seeing some of these aromatic molecules. So that paves way for the new theory, bottom-up chemistry, where we think that simple molecules and atoms had enough energy in their environment inside of these clouds to combine to form these simple aromatic molecules such as benzene and benzonitrile, etc. This is supported by the fact that this is how we see most chemistry happen. Most molecules and compounds that we know of form this way from the bottom up. And so where I came in was to look further, try to find benzonitrile in more sources so we can start to piece together where this stuff is happening. So, how do we find them? We use what's called spectroscopy. When photons come in and hit an atom or molecule, they can excite that atom or molecule from a low energy state to a higher energy state by getting absorbed into the atom or molecule. In what I'm looking at is called rotational spectroscopy, where this happens by increasing the rotational speed of a molecule. When the molecule is then at a higher energy state, and that state is less stable, so it can spontaneously drop to a lower energy state by re-emitting a photon of a particular wavelength. So if we can correctly model how a molecule behaves, and we can figure out what frequencies of light it will emit, and we can look for those frequencies in a source and see if they line up with the molecule we're looking for. For example, here are the electronic spectral lines, which is slightly different because they appear in the visible light spectrum and are caused by electrons jumping for hydrogen, mercury, and neon. The main problem with rotational spectroscopy is it requires something for the photons to interact with. So there needs to be an unequal charge distribution in the atom. However, benzene, is perfectly symmetric and therefore doesn't interact with light much at all. And so what I used is benzonitrile, the picture on the right here, which is very similar to benzene and appears in the same places that benzene does appear, but has this extra carbon nitrogen group attached to the side of it, which causes it to interact much more strongly with photons. So now that we have a means to look for these, what data am I using? Well, I'm using data collected by the Green Bank Observational Telescope, and this data was collected by the group Gotham and its sister group Arkham. Gotham looked inside this one specific cloud called and this one specific subsource inside the cloud called TMC1, whereas Arkham looked over a variety of around 20 sources and has already published papers on the 4 sources listed there. Where what I did was I started going through the Serpent's Cloud and went on to the next source inside the Serpent's Cloud to look for benzonitrile. So this is what the Serpent's Cloud looks like, and this image is taken in the infrared. And so in the infrared, we see these black bands across the picture, and these black bands correspond to areas in space that are absorbing energy, and so they appear darker in the image. So these dark bands are actually the intermolecular dust clouds that I was describing earlier. And these white contour lines represent where the most of the radio emissions are coming from this cloud. And so that is how the cloud got subdivided into these different areas. The previous paper released by Arkham found benzonitrile in 1A, 1B, and 2. I expanded the search by looking for benzonitrile in the next source, Serpens 3A. And so what did I find? Well, the data you see here is the 4 different frequency bands that Arkham collected on Serpens 3A that they believed would line up with the strongest lines of benzonitrile. And in the red is what a model predicted, tried to match benzonitrile's spectroscopy frequencies to the data. And so, as we can see, there's some clear evidence of peaks here. However, those peaks they fall well below the noise level, so we need to do some operation to filter this data and reduce the noise level. We do that through a process called spectral stacking, where we take a small range of the frequency values that we detected around each of those simulated benzonitrile lines, and we add them. In places where the data is purely random, this data should destructively interfere and lower the noise level. Whereas if there's benzonitrile here, then the data at each of these peaks should additively interfere and build a stronger peak. And so that is what we see on the image on the left here. That is the stack. And so we see there's some clear evidence of a peak here. But to figure out how significant this is, we need to see how well this correlates to the data at every single point. If we take this signature for benzonitrile and we pan it across the entire data set for Serpens 3A, then and measure how much it correlates at each point, then at the places where it doesn't line up with what the model believed benzonitrile lies at, then it should not correlate well and should have a low random correlation. However, at the one point where it lines up perfectly with the model's prediction of where benzonitrile is, it should have a strong peak, and the height of this peak will tell us how significant the finding is. That's what we see on the right here. This gives us a value of 6.3, which correlates roughly to statistical significance, and generally anything greater than a value of 5 is accepted in the field. So in conclusion, I found benzonitrile in Serpens 3A. What this means going forward is that we need to keep looking. We need to go through the rest of the locations inside of Serpens, try to find benzonitrile in all those, and look in sources outside of Serpens and see where we do, and just as importantly, where we don't find benzonitrile, and therefore benzene and a whole slew of other aromatic molecules. Some final thoughts. Here on the left is some of the model's findings compared to findings published by the Arkham paper. In this NCOL column, the column density, this corresponds to how much of a molecule appears in each of these areas. And as we can see, benzonitrile appears to appear more frequently in Serpens 3A than any of the previous 3 sources. And so something going forward that I can do is look into why benzonitrile might be more prevalent in Serpens 3A as opposed to these other sources. In this second column, in this other column here, the excitation temperature in Kelvin is the energy at which benzonitrile, the cloud gets excited and starts releasing energy. And as we can see, my data value falls roughly in line with the other sources, and so that was to be expected. On the right here, we can also see a corner plot, which represents how much the different parameters in my model correlated with each other. A small, well-compacted figure shows good correlation, and as we can see here, the column for source size is very poorly condensed. It's very spread out. What this likely means is that this cloud isn't it's not a great model to define this cloud that I'm looking at as one source, and it's better to treat it as multiple separate sources, each of which has their own parameters. And so something else I can do going forward is reanalyze this cloud, giving the model more parameters to work with to try to create a better simulation. And that is everything I had to talk about. Thank you very much.